Hello and welcome to the TI Precision Labs hands-on experiment covering amplifier settling and charge bucket filter design. In this experiment, we will use the Analog Engineer's calculator and simulation to predict the ADC settling. We will look at several examples, some that are properly designed and others that have poor settling. For each experiment, we will simulate the settling and measure the AC performance. In the last Precision Labs lecture, we described in detail the steps involved in selecting the SAR ADC amplifier and associated filter. For this lab, we will quickly review and summarize this procedure. We will use the Analog Engineer's calculator to find the bandwidth and initial values for the RC circuit. Next, we will optimize the circuit using TinaSpice. Finally, we will measure the performance of the properly designed circuit as well as the poorly designed circuits. First, let's quickly review the design problem that we covered in the lecture. The goal here is to choose an amplifier and find the final values for the filter. For the amplifier, we want to get a rail-to-rail input and output without crossover distortion. We can get the bandwidth of the amplifier from the Analog Engineer's calculator and use the parametric search to find a good amplifier choice. Finally, we need to test the amplifier's model to verify that the output impedance and open-loop gain curve are correctly modeled. For the charge bucket filter, we need to use the initial values from the Analog Engineer's calculator as a starting point in TinaSpice to optimize component values. We will use parameter stepping to find the RC value that gives the best settling. Let's review the operation of the Analog Engineer's calculator. First, find the ADC SAR drive calculator under Converters. Next, select Single-Ended 2 and enter the resolution, internal sample and hold capacitor CSH, full scale range, and acquisition time. Note that all this information can normally be found in the ADC's datasheet. Press OK and the range of R-Filt and C-Filt will be displayed. In this case, the resistance range is from 4.1 ohms to 32.5 ohms, and the nominal filter capacitance is 1.1 nanofarads. Also, the amplifier's bandwidth is given to be 17.8 megahertz. Based on the gain bandwidth product and the fact that we need a rail-to-rail amplifier without crossover distortion, we used parametric search to choose the OPA 320 for this example. Pause now and try this example on the Analog Engineer's calculator. Now let's confirm that the OPA 320's op-amp model is accurate. Specifically, we will check the open-loop gain and output impedance models. Both of these parameters are very important in ADC settling. This slide shows the standard test circuit for open-loop gain testing. The terafarad and terahenry components are used so that the simulation has a closed-loop DC operating point, but is open-loop to AC. Pause now and run the example TINA file AOL OPA 320 TSC. Compare the result to the datasheet specification. Another important curve is the open-loop output impedance. This curve is ideally flat for fastest ADC settling. The circuit used for this test is similar to the open-loop gain test, as the feedback loop is broken for AC but shorted for DC operation. The main difference is that the current generator signal source is applied to the output of the amplifier. Pause now and run the example TINA file ZO OPA 320 TSC. Compare the results to the datasheet specification. Now that we have verified that the amplifier's model is accurate, we can use simulation to adjust the RC charge bucket filter for optimal settling. Here we will use parameter stepping to sweep the resistor value from 4.1 ohms to 32.5 ohms. The capacitor value will be held constant at 1.1 nanofarads. Note that the two resistors are actually voltage-controlled resistors. This scheme was used as parameter stepping can only control one object at a time. The voltage source value is equal to the resistance of R-Filt1 and R-Filt2. The objective of the parameter stepping will be to get an error signal that is less than 1/2 LSB at the end of the acquisition cycle. In this example, 1/2 LSB is 38.15 microvolts. Let's look at the simulation results. Here we see 3 different iterations of the parameter stepping for this example. In the first iteration, we sweep the resistor according to the range from the Analog Engineer's calculator. That is, we sweep the resistance from 4.1 ohms to 32.5 ohms. We use the 3 best settling results from this simulation to set the range for the next simulation. Typically, these results will contain an overdampened and underdampened response. In this case, the boundary is adjusted in the second iteration from 19.9 to 26.3 ohms. Again, we use the best 3 settling results to set the new boundary. However, in the case of the third iteration, we use standard resistor values in the parameter step table. The result of the third iteration gives the optimal resistor value for best settling. Pause and run the parameter step simulations. For this experiment, we will be using channel 2 on the Precision Labs hardware. First, set the jumpers as shown here. Connect the PSI to the PLabs board using the SMA cable and connect the PHI to the PLabs channel 2 connector. Finally, connect the USB cables to the computer. Throughout this experiment, we will test different amplifiers. Always be careful to install this amplifier right side up with the label at the bottom of the coupon card. For now, you can leave the amplifier socket empty. Pause and connect the hardware. Throughout the experiment, we will use different devices and apply different input signal amplitudes at different sampling rates. Also, we will simulate and measure the performance of the different circuits. Print out this table and use it to record your measured results as you step through the experiments. Now start the software by selecting the PLabs SAR EVM icon on the Start All Programs menu. Once the software is running, you should notice the green Hardware Connected message at the bottom of the software. Also, if the PSI controls are colored teal, then the hardware communications is working. Pause and get the EVM software started. The circuit shown here uses the values that we found in the parameter step optimization. Remember, the goal was to get the settling error less than the 38 microvolt error target at the end of the acquisition period. The settling error for this design is about 28 microvolts, which meets the goal. Since the settling error meets the goal, we expect the system performance to be equal to the ADC datasheet specification. For reference, let's call this design OPA 320 Good Filter 1. Pause now and run the ADC input settling simulation. Now let's measure the performance of Good Filter 1. First, install the OPA 320 Good Filter 1 coupon board in the channel 2 socket. Be careful to properly align the pins and make sure that the device is right side up. Second, set up the PSI. The amplitude is 4.9 volts, the offset is 2.5 volts, and the frequency is set to 2 kHz. Press the power button to enable the output. Third, press Capture. The FFT results will be displayed under Spectral Analysis. Fourth, record the AC performance and compare it to the expected datasheet performance for the ADS 8860. The ADS 8860 specified SNR is 93 dB and the THD is -108 dB. The measured AC performance of this circuit actually exceeds the datasheet specifications. This proves that the amplifier and associated filter are properly designed. Pause now and test the performance of Good Filter 1. In this experiment, we will intentionally choose wrong values for the RC charge bucket circuit to see how performance is affected. Here we use 100 ohm resistors rather than the 24.9 ohm resistor value determined during our Tina Spice optimization. You can see the simulation result shows that the settling error is -41 millivolts, which is more than 1,000 times larger than the error target of 38 microvolts. For reference, let's call this design OPA 320 bad filter. You can verify the simulated performance later using the included file. Now let's measure the performance of the OPA 320 bad filter circuit that we just simulated. First, install the OPA 320 bad filter coupon board and the channel 2 socket. Be careful to properly align the pins and make sure the device is right side up. Second, set up the PSI. The amplitude is set to 4.9 volts, the offset is set to 2.5 volts, and the frequency is set to 2 kilohertz. Press the power button to enable the output. Third, press Capture. The FFT results will be displayed under Spectral Analysis. Fourth, record the AC performance and compare it to the expected datasheet performance for the ADS 8860. The ADS 8860 specified SNR is 93 dB and the THD is -108 dB. The measured AC performance of this circuit is very poor compared to the datasheet specifications. For this example, we measured 82.5 dB for SNR and -73.4 dB for THD. Also, you can see significant noise and harmonics in the spectral analysis FFT results display. This emphasizes the importance of using the parameter stepping optimization we covered earlier to select the optimal RC charge bucket circuit. Pause now and test the performance of the OPA 320 bad filter circuit. In this experiment, we will intentionally choose an amplifier with insufficient bandwidth to drive the SAR ADC. Here we use an OPA 333 op-amp with a bandwidth of 350 kHz. Remember, the bandwidth requirement from the calculator was 17.8 MHz. You can see the simulation result shows a settling error of -88 millivolts, which is more than 1,000 times larger than the error target of 38 microvolts. For reference, let's call this design OPA 333 low bandwidth. You can verify the simulated performance later using the included file. Now let's measure the performance of the OPA 333 low bandwidth circuit that we just simulated. First, install the OPA 333 low bandwidth coupon board and the channel 2 socket. Second, set up the PSI. The amplitude is set to 4.9 volts, the offset is set to 2.5 volts, and the frequency is set to 2 kilohertz. Press the power button to enable the output. These settings are the same as in the last experiment. Third, press Capture. The FFT results will be displayed under Spectral Analysis. Fourth, record the AC performance and compare to the expected datasheet performance for the ADS 8860. The ADS 8860 specified SNR is 93 dB and the THD is -108 dB. The measured AC performance for this circuit is very poor compared to the datasheet specifications. For this example, we measured 54.1 dB for SNR and -55.9 dB for THD. Also, you can see significant noise and harmonics in the spectral analysis FFT results display. This experiment emphasizes the importance of using an amplifier with sufficient bandwidth. Pause now and test the performance of the OPA 333 low bandwidth circuit. In this experiment, we will look at another amplifier that has insufficient bandwidth to drive the SAR ADC. Here we use the OPA 316 op-amp with a bandwidth of 10 MHz. Remember, the bandwidth requirement from the calculator was 17.8 MHz, so the 10 MHz bandwidth of the amplifier is close but not sufficient for this sampling rate. You can see the simulation result shows a settling error of 35 millivolts, which is substantially larger than the error target of 38 microvolts. Note that this amplifier has input crossover distortion, and a hands-on experiment covering the effects of crossover distortion is covered in a different video. For reference, let's call this design OPA 316 crossover. You can verify the simulated performance later using the included file. Now let's measure the performance of the OPA 316 crossover circuit that we just simulated. First, install the OPA 316 crossover coupon board in the channel 2 socket. Second, set up the PSI. The amplitude is set to 3.6 volts, the offset is set to 1.8 volts, and the frequency is set to 2 kHz. Press the power button and enable the output. These settings are different from the last experiment. In this case, we reduce the amplitude of the input signal to avoid the crossover distortion region. We will discuss this more later. Third, notice that the default sampling rate is set to 1 megasample per second. Fourth, press Capture. The FFT results will be displayed under Spectral Analysis. Finally, record the AC performance and compare it to the expected datasheet performance of the ADS-8860. The measured AC performance of this circuit is very poor compared to the datasheet specifications. For this example measurement, we measured 86.1 dB for SNR and minus 85 dB for THD. Also, you can see significant noise and harmonics in the Spectral Analysis FFT results display. This experiment emphasizes the importance of an amplifier with sufficient bandwidth. In the next experiment, we will reduce the sampling rate to see how performance is affected. For now, let's pause and test the performance of the OPA 316 crossover circuit. If you switch to the time domain display, you can see that the maximum voltage of the input signal is 3.5 volts. The input signal amplitude was selected to avoid the crossover distortion region, which is at 3.8 volts. Thus, any AC performance limitations we are seeing is not from crossover distortion. If you aren't familiar with crossover distortion, please watch the crossover distortion experiment given in the link below. Reducing the sampling rate will cause the acquisition time of the SAR ADC to increase. This will make it easier for the data converter to achieve good settling, which allows lower bandwidth amplifiers to achieve good settling. For the next experiment, we will reduce the ADC sampling rate to 500 kHz. This slide shows how to calculate the new acquisition time based on the reduced sampling rate. First, note that the period of the entire conversion cycle is 1 divided by the sampling rate. In this example, 1 divided by 500 kHz is equal to 2 microseconds. Next, note that the maximum conversion rate is a fixed value. For this example, it is 710 nanoseconds. Finally, note that the acquisition time can be calculated by subtracting the maximum conversion rate from the entire period. In this example, 2 microseconds minus 710 nanoseconds is equal to an acquisition period of 1.29 microseconds. Remember that the acquisition time for a 1 MHz sampling rate is 290 nanoseconds. So decreasing the sampling rate to 500 kHz significantly increases the acquisition time. Now let's use the acquisition time that we just calculated in the Analog Engineer's calculator. The resolution, sample and hold capacitor, and full scale range are the same as before. After pressing the OK button, you can see that the gain bandwidth requirement is now 4 MHz. Since the OPA 316 has a gain bandwidth of 10 MHz, we should be able to get good results for this device. Let's simulate the performance. Here we have the same circuit we looked at in the last experiment. The only difference is that we adjusted the sampling rate to 500 kilosamples per second. With this new sampling rate, the amplifier bandwidth should be sufficient for good settling. Sure enough, after the simulation, you could see the settling error is about 47 microvolts, which is comparable to the error target of 38 microvolts. You can verify the simulated performance later using the included simulation file. Now let's measure the performance of the OPA 316 crossover circuit that we just simulated. First, no change is required on the hardware. We are still using the OPA 316 crossover coupon board in the channel 2 socket. Second, set up the PSI. The amplitude is set to 3.6 volts, the offset is set to 1.8 volts, and the frequency is set to 2 kHz. These settings are the same as in the last experiment. Press the power button to enable the output. Third, set the sampling rate to 500 kilosamples per second. This lower sampling rate should allow for better performance. Fourth, press Capture. The FFT results will be displayed under Spectral Analysis. Finally, record the AC performance and compare it to the expected datasheet performance of the ADS-8860. The measured AC performance of this circuit is close to the datasheet specifications. For this example, we measured 90.3 dB for SNR and minus 102 dB for THD. You could see significant improvements in AC performance compared to the same circuit with the 1 MHz sampling rate. Thus, it is possible to use lower bandwidth amplifiers and get good performance if you reduce the sampling rate. Pause now and test the performance of the OPA 316 crossover circuit with a 500 kHz sampling rate. You may have noticed that although the error settled to the target in the last experiment, the settling had a lot of overshoot and ringing. Ideally, for best performance and a robust design, the settling waveform should have minimal overshoot and ringing. The top graph shows the settling of the previous circuit, which wasn't optimized. Using a SPICE parameter stepping optimization, you can find better values for the RC charge bucket circuit. The bottom graph shows the final optimized transient response. Notice that the settling waveform has no overshoot and settles to a small error of 40 nanovolts. Again, for the best performance and a robust design over temperature and process variation, use the optimized RC charge bucket values. This table summarizes the results for all the experiments and simulations. For simulations, the settling error should be less than 1/2 LSB or 38 microvolts. If you look at the results, the only simulations that are close to the error target are for experiments 1 and 5. All other experiments have errors in millivolts, which is substantially larger than the error target. Notice that the measured AC performance in the example measurements is very good in cases where the settling error is small. Remember, the ADS 8860 datasheet performance is 93 dB for SNR and -108 dB for THD. If you look at experiments 1 and 5, the circuit approaches this performance. Comparing the performance for the other experiments shows significant performance degradation. Thus, the settling results in the simulations correlate well to the measured AC performance. The conclusion of this experiment is that it is important to select amplifiers with sufficient bandwidth and also choose the optimal RC charge bucket component values for best settling and AC performance. That concludes the hands-on experiment. I hope this was useful to you. Thanks for your time.